Hi, this is Mr. Ward. I'm going to do a video key for Do Now 19.3, week 19, day 3 for geometry. So first things first, you're going to need these theorems that I introduced in the last Do Now and exit tickets. Theorem 22 and 23, and the definition of a perpendicular bisector. So let's review those for a second. Definition: the perpendicular bisector of a segment is the line that bisects and is perpendicular to the segment. So it bisects and it is perpendicular to the segment. So it is the line that bisects and is perpendicular to that segment. So that leads us to a couple of theorems, which are really just they're definition theorems because they're reversible. If Theorem 22, if 2 points are each equidistant from the endpoints of a segment, so that means like I have this point, and let's say I have this segment, and these 2 points are equidistant from this segment. So I can draw this congruent line segment and this congruent segment. Brilliantly done, I know. And this one and this one. Then those 2 points, if these 2 points are equidistant from these endpoints of the segment, then these 2 points determine the perpendicular bisector for that segment, which means they are 2 points you could draw a line through. And if I had done the points right, it would have worked here. I'll fix that real quick. Here's fudge factor. Okay, so those 2 points will determine the perpendicular bisector for that segment. So it's split into 2 congruent parts. By the way, one of the points could have been right here. Let me actually grab a different color for this. One of the points could have been here. It could have been this point. This point happens to be equidistant from the endpoints too. So this point and this point, this point and this point, right here, this point and this point, any pair of those which happen to be equidistant from these endpoints would work as 2 points to determine a line that is the perpendicular of a segment. Now let's take a look at the Theorem 23, which you'll also probably need. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So we'll draw another situation. Here's our segment, and we'll draw a perpendicular bisector. Okay, here is a perpendicular bisector. It is a line, and it happens to be perpendicular to that. So these are things that we know from this little statement. We know that this segment and this segment are congruent because this purple segment has been bisected. So what this is telling us is that any point that we plot on our perpendicular bisector, which is in green, any point I plot on there is equidistant from the endpoints of this segment, which, by the way, means that you can produce endless isosceles triangles. So this point here is equidistant. This point here is equidistant. So that is an isosceles triangle, by the way. This point here is equidistant. Every single point on that perpendicular bisector. If it's on the perpendicular bisector, that's the key thing. If the point is on the perpendicular bisector, then it is equidistant from the endpoints. So like those are equidistant. Those are equidistant. Every single point, forever. Okay, so I hope that clarifies a bit about what the Theorem 22 and 23 are about. So here you're going to need Theorems 22 and 23 for this one. So we have some information. We know that PM bisects BC. So PM bisects BC perpendicularly. Okay, so this symbol is perpendicular. This is for bisection. So it's a perpendicular bisector for BC. given. Okay, so that's our first statement and first reason. AB is congruent to, to AC. Okay, given. Okay, so let's label what that means real quickly. So AB and AC are congruent. Now we can then add some information. We can say, well, this bisects BC, then we can say that BM is congruent to CM by definition of a bisector. Okay, it's a perpendicular one, but any bisector would split that into congruent segments. So let's go ahead and mark those up. So that is congruent to that. Okay, so we've already been told that PM are the line is PM, and it's being determined by P and M. But now we have this additional information. We know that A is equidistant and M is equidistant. So we can now say the line MA determines a perpendicular bisector. You spell that right, of BC, because both M and A are equidistant to the endpoints of BC. Okay, and then we can finally say that A lies on the perpendicular bisector of BC because it is one of the pair of points that determine the perpendicular bisector of BC. Okay, so that works as a proof. You could have worded it differently than that, but that's what I came up with. Once we know A is equidistant and M has to be equidistant because of definition of a bisector, then we can add that both M and A are on the perpendicular bisector. And since PM is the perpendicular bisector, PM has to pass through A because it's the same line as MA, also the perpendicular bisector. There's only one perpendicular bisector of a segment, at least in two-dimensional space. That changes if you're three-dimensional. So how did this proof in 1A provide support for Theorem 24 below? So Theorem 24 says, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. So let's draw what that means. So here we have a segment, and there is some perpendicular bisector of that segment, okay? And it goes like that, and it is perpendicular, and this segment is bisected. So it's in two congruent parts. So if a point is equidistant, so let's plot some point way out here, and we're going to say this point here is equidistant to these endpoints. If that is true, then we can extend this line, the perpendicular bisector, through that point. We know that point will be on that perpendicular bisector. This is called the lies on theorem because it lies, we're talking about a point that lies on the perpendicular bisector. So how did our proof in 1A provide support to 24? So let's look at our proof. So what we worked out was a way to combine basically theorems 22 and 23. M is on the perpendicular bisector, so it's equidistant from the endpoints. P is also, by the way, And then, so if it is on the perpendicular bisector, then it's equidistant. So that's theorem 23. So let's go ahead and maybe add that note here. So I'm going to add the note that M is equidistant to, actually, this is sort of redundant. We could do either one, actually. So I'm going to say it this way. Or M is equidistant to C and B by theorem, by being on the perpendicular bisector. Theorem 23. Okay, and then we also know that this one here, MA determines a perpendicular bisector because both M and A are equidistant. So we can add that is theorem 22. If 2 points are each equidistant, then they determine the perpendicular bisector. So that is just a statement of theorem 22. No, not 23, 22. So at any rate, what we've done is we've combined the information that is contained in theorem 23, that if something's on the perpendicular bisector, then it is equidistant to the endpoints. And then if something is equidistant to the endpoints, then it and another point that it has the same features is something that determines the perpendicular bisector. So theorem 23 demonstrates that M is equidistant because it's on the perpendicular bisector. And now we have 1 point that's definitely on the perpendicular bisector. And then A is equidistant. So the combination of A and M can put together a line for the perpendicular bisector. Okay, so we combined theorem 23's assertion that a point on the perpendicular bisector is equidistant from the endpoints of a segment that is perpendicularly bisected with theorem 22's assertion that 2 points that are equidistant from the endpoints of a segment that has been perpendicularly bisected determine the perpendicular bisector. Actually, I don't even need to say that they're equidistant from the endpoints of a segment. That is unnecessary. That they determine the perpendicular bisector. Okay, and with that information, then we can combine those 2 points into another name for the line that is the perpendicular bisector. Okay, I hope that helped, and I will stop now.